Okay, we're starting this again here. We're talking optimization, which means we're finding absolute maximums and minimums throughout this. You're going to see different kind of problems. Today's area and what I call business problems. We're going to try to maximize profit, minimize cost, that kind of thing. We'll do volume problems. Then we'll hit some, if you increase the price, what happens if you, how many you sell. And then last but not least, we'll be finding some optimum routes to get from place to place. So these can be used in lots of different places. But as far as talking about where you're going to use calculus in the real world, this is it. So if you're looking at your example optimization problems, you will see that number one is got a basic farmer here. And our farmer, I need a rectangle without... Use square coordinate rectangle that has no fill on it. No fill. There we go. That'll do. All right. So he's going to build his rectangular field, but he wants to put fences down the middle. So I'm going to make myself a nice little rectangular field here, and then we're going to throw some fences in the middle of it. Attempting. So he essentially wants to end up with 3 pens in here. Okay, now this guy, though, I'm sure some of you who are connected to farmers know that sometimes they're very economical. In this particular case, he has 3,000 feet of fencing on hand, and he does not want to buy any more fence. He's using only the fencing he's already got in stock on the farm. Okay? So the question is, what dimension should he use for the perimeter so that he optimizes it and gets the largest possible area inside the fence? So he wants the most area inside it, but we're trying to find the outside dimensions. So as you set these up, you need, of course, you're going to need a picture, and you're going to need to label it with variables. So what variables, and label them with common sense variables here. It'll help you a bunch. Length and width sounds good.
Yeah, that's a good one.
Yeah. So the long direction is length, and the short direction is width. Okay. What is it you're trying to optimize? What is it wants you to find the maximum or minimum of?
Area.
It says the last 3 words, largest possible area. So you are trying to find area. You're always going to have one function, which was whatever they say, to maximize or minimize. If that function contains 2 variables, you will have to have another equation, because we only want to work with 1 variable when we go to find our absolute maximum or minimum. We don't want a 2-variable equation. So we need another equation that relates those 2 variables so we can sub it in here and get this thing to become a 1-variable equation. So we have to figure out something else we know that relates to lengths and widths. Well, what's the other piece of information they gave us in the problem? He's got 3,000 feet of fence to use. So, what has that up to be 3,000 feet?
4 times 2L.
Okay.
4L times 2. 2L plus 2W. No, because you got to have it split. 4W plus 2L.
Okay, so are we narrowing that down? Because you're saying we got to have, even though the width, those fences down the middle aren't affecting our area, they are affecting how much fence we use. So you really do have 4 W's in this problem and 2 L's. So I'm going to have 4 W's plus 2 L's equals what? 3,000. So your second equation has to be something that equals to a number. You actually have to have a numerical value. The first one is a function, A for area. But the second one's got to be equal to an actual value. Then you're going to want to try then to get it all into 1 variable. So I actually also wanted to make you a set of steps here, and I wrote that too far out. So as far as steps go, first thing, draw and label a picture.
steps are?
Last time I did this, I had 8 steps.
Got it, so make it
So then you need to write the formula for the function to be maximized or minimized. Okay. So how do you know if you need a second formula? Yeah. Write a second equation if more than one variable. Now, this next step, I'm going to tell you to do it now because I think people forget to do it, or you get so involved in the problem, you ignore it, and then it's... If you forget to do this and the steps that follow from it, you would be losing 5 points on every problem. So this is not something you want to forget to do. So I'm going to tell you right now. Do you remember when we did absolute maximum and minimum problems? They gave you a function to find the maximum or minimum, and they gave you something else. An interval. And you remember, depending on whether it was brackets or parentheses, you have to come up with an interval, but this is a common sense, real world interval. They're not going to hand it to you. You got to figure it out. So, you so
3,000. No.
so identify the interval. Okay, the interval. We're talking common sense here. The interval is going to be, actually, I should not have had you done that. That should be step 5, sorry. I need to have you do, we got to pick a variable first before we write an interval. So, first we need to change the equation to one, change the function, should say, to one variable. Because you do have to know which variable you're writing your interval for before you can write it. So, it doesn't matter which variable you change it into. We need to turn area into all lengths or all widths. Me personally, I try to do what's going to make my algebra easiest. So, over here in the 4w plus 2l equals 3,000, which variable is going to solve out nicer if I try to isolate that variable? If I solve for w, I'm going to end up dividing by 4. If I solve for L, I'm going to end up dividing by 2. If I end up dividing by 4, I'll end up with L being 1/2, because I'll have to divide it by 4 too, I'll end up with fractions. 2 divides into everything, doesn't it? So I would do the 2L, because then I won't end up with fractions. So I would be subtracting my 4W over, and divided by 2. So we have a nice round 1,500 minus 2W. That's pretty sweet and easy to work with. So what am I going to do with it? I'm subbing that in for L. So 1,500 minus 2W times W is going to be 1,500W minus 2W squared. All right, so we have an equation all in W's. That's what we need to know. Now do your interval. It's crucial that you don't forget to do this. And this is for most people, finding their interval is the hardest part. Okay, the interval's common sense. How small could W be? Could the width equal 0?
It could be approaching 0. It could be a straight line of wire.
It could be approaching 0, but would it have any area? No, we have to have a rectangular area. So the width can't be 0, but it could be
very close to 0.
Yeah, some tiny fraction. Obviously, that's probably not what we want. But so yes, it's going to be parentheses 0.
Very skinny cows.
Some very skinny cows, yes. Now it's the high side that drives us crazy. The low side is a lot of times 0. Occasionally, they will in the problem tell you it has to have the minimum width is 20 feet or something, and then you have a minimum that gives to you. But otherwise, a lot of times, it'll be 0 with a parenthesis. Okay, so what's keeping me from just having this infinitely big area?
3,000.
My 3,000 feet. This equation you wrote equal to the 3,000, that's your limitation. That's what's going to help you find the high side of your interval. Okay, remember, we want to know how big W can get, because we're solving our problem in W's, so we're wanting to know how big W gets. Go back to this original one equal to 3,000. If I want W to get big, what has to happen to L? It's got to get small. So if you let L go to 0, that would be really small. That would take the 2L out of there. So you have 4W equals 3,000. How big can W be then? If I divide by 4, 3,000 divided by 4 is 750. So it will be 750 with a print, because it can't get clear to 750. That would still be no area then, but it can get really close to 750. So when you want the high side of your interval, you have to sub 0 into the opposite variable. Okay. I should say identify variable or identify interval for variable in problem. Okay. So now, we've done the hard part. We have the function set up. We've got an interval. How do I find a maximum? This is now all just the curved, sketchy calculus that you already know. Yeah, you have to find critical points, don't you? Because we know maximums and the minimums are critical points. So here we are. Find the critical points. Shania, behind you. Okay. So, yeah, find critical points. How do you find critical points? You do a derivative, and these aren't going to be the tricky, nasty, mean derivatives for the most part. And at bare minimum, you might see a product rule once in a while, but most of these are going to be pretty easy derivatives. So 1,500 minus 4W, I set it equal to 0, and I solve it. And 1,500 divided by 4, I believe, is 375. Okay, first thing to check, is that critical point in the interval? It's got to be in the interval. If it wasn't, you'd pitch it out. It's not valid. Can't do that. Okay, now, okay, this is where people quit, because probably 90% of the time, that critical point will be your answer. But occasionally there are problems where it's not your answer. And I know how to rig problems to make it not be your answer. Okay, so you still have to verify for me that that's the absolute maximum, because we wanted it to make maximum area. So how did you do absolute maximum minimums when the interval had parentheses? You had to do limits. So if it's got parentheses on it, I have to do the limit as W approaches 0 of which function? I got like a bazillion different equations up here. Which one am I doing the limit on? The one right before your derivative was your original function. All in one variable, right here, all in one variable. The one right before the derivative is the one you're going to do, that's the function you're going. Okay, so this is incredibly difficult. How do I do a limit approaching 0? You sub 0 in, and you get 0. I need more space. Oops. Let me go down a little bit. Okay, and then if I do the limit approaching the other side of my interval with 750, you'll discover if you sub 750 in for this, you will also get 0. Okay, so what does that mean in terms of our finding an absolute maximum?
You just find what that equals. You said 375, and that's your area.
Okay. We need, for 375 to be the maximum, we need it to come out with some number bigger than 0. Because if you recall, we would usually do a little t-table action, and we would throw In this case, 375 is our critical point, and we would put it in which, once again, which equation? The one we're calling our original, this one right here before the derivative, that's the original function. That's what you're shoving everything into. If you put 375 into that, you get 750. Okay. From here on out, though, we usually don't write it as t-tables. Instead, what we usually do is we say, I'm going to put 375 in the function, and I get a value of 750. Because we're really not graphing it this time, but it's the same idea. Okay, is 750 bigger than our limits? Yes. So therefore, 375 is going to give us the absolute maximum value. Now, the last thing to do is go back and ask yourself, did I answer the question the problem asked? What did the problem want as an answer? It wants the dimensions of this thing. So what's 375? 375 is the width. I need width and length. Where can I go get the length?
Just take 3,000 minus, sub it in 4W plus 2L.
It's the 4W plus 2L. Actually, right here where you isolated it, you'll have it isolated when you subbed it into the other function. It's sitting right there. So you're putting it in this L equals 1500 minus 2W. So if L equals 1500 minus 2W, all I need to do is sub 375 in there, which would be multiplied to 750. And so when you subtract 1500 minus 750, you get 750.
So is the perfect square going to be like the maximum most will have?
If it was just a particular rectangle, then yes, the perfect square is always the maximum area. But because we have these fences down the middle, that totally changes it all. So you would say then it's going to be 375 feet by 750 feet. And if I've asked this question a million times, how do you know which one to write first when you're doing dimensions? Because I don't know. But when you set this up, how did you know for sure which one was it the L's or the W's going to be longer? So
It's a rectangle. It doesn't matter. Which one goes here?
I am good. Write me dimensions. I don't care which order. All right. And today you have solved your first optimization problem.
That's a lot of. So we've got about 2 big areas.
Yeah.
Big.
Well, 3,000 feet. Think about it. 3,000 feet. That's over half a mile.
Yeah.
That's a lot of fence.
Yeah, but you gotta go.
Yes, we need to finish the steps. Okay, I just have 2 more. So we found the critical points. What did you all do after we found 375? If it was parentheses, if it had been brackets, what would you have done? You would have subbed the endpoints in on the interval and the critical point and to find out which one came out biggest. So I'm just going to say, and it depends on whether you have brackets or parentheses, so I'm just going to say test the critical points and endpoints.
So if it does give us a minimum, then that would actually be included, right? Like you can just bracket them. Like if the minimum should be
Yeah, if they've given you a minimum, they said it has to be, the dimension has to be at least 50 feet wide, then you would start at 50 with a bracket instead of a 0 with a parenthesis. They told you there's a minimum size to it. Okay, and then finally, once you've tested that, we'll just say calculate and write final answer. So, granted, this was just a little area problem, but if you think about this kind of use in the real world, people want to know how to do these types of problems. This is big. Just, particularly when we start maximizing profit and cost and all that good stuff. Okay, I don't want to work problem 2 all the way out. I just want to show you how this same problem could get set up in a different manner.
This is my
Yeah.
time.
Oh, thank you. Yikes.